Now, after deriving the equation of kinetic energy, potential energy and mechanical energy for a simple harmonic oscillator, what should be the shape of the graph of the kinetic energy, potential energy and mechanical energy for a particle performing simple harmonic motion? For that purpose, we are going to do the graph of energy versus displacement like this manner. So we consider the energy on y-axis and displacement on x-axis. Now listen, the equation of the kinetic energy is half k square. Half k square. And equation of the potential energy is half k square into cos square omega t plus phi, and equation of the kinetic energy is half k square sin square omega t plus phi. Therefore, the kinetic energy is, and also we discussed about that, at mean position the kinetic energy is maximum, and at extreme point the kinetic energy is 0. So there is the x is equal to plus a point, there is the x is equal to minus a point, and there is the x is equal to 0. Here the oscillator performs the simple harmonic motion on linear path. There is the mean position, and these 2 points corresponding to the x is equal to plus a and minus a are the extreme point. Kinetic energy is maximum at mean position, and at the extreme point there is 0. So there is the graph of kinetic energy. While the potential energy at mean position, the potential energy is minimum, and at extreme point the potential energy is maximum. Therefore, the graph of potential energy is this way. That is the graph of potential energy. The addition of these two energy, that gives the total energy of the mechanical energy. Therefore, the mechanical energy is this total energy. So there is the graph of energy versus displacement x. Now from this graph, the kinetic energy is independent of the position, and that remains the constant. Now the total energy or mechanical energy remain constant. It does not depend on position of the particle. Its graph is linear. While the kinetic energy and potential energy are parabolic. That means the shape of the graph of the kinetic energy and potential energy is parabolic. Kinetic energy is maximum at mean position. That means the x is equal to 0 position, and minimum, that means 0, at extreme point S is equal to plus or minus A points. While opposite to that, potential energy is maximum at extreme point corresponding to the x is equal to plus or minus A, and minimum, that means the 0, at mean position, that means the x is equal to 0 position. Clear? Both are the pair bodies. That means the kinetic energy and potential energy continuously changes with time. The periodic time of kinetic energy and potential energy is E by 2. Within the one period of oscillation, it becomes the twice time maximum and twice time 0. Clear this? Now the point at which the kinetic energy and potential energy becomes the equal. At that time, the position in the x is equal to plus or minus A upon root 2. The point at which kinetic energy and potential energy becomes equal. The position is x is equal to plus or minus A upon root 2. That means this point, the kinetic energy and potential energy becomes equal. So these are the points of the graph of the kinetic energy and potential energy. Clear this thing? Okay. Okay, now the next question is that what are the oscillations produced by the spring? That means as we take the one object at the free end of the spring and slightly we displace this object from its equilibrium position and release, so it performs the oscillation. These oscillations are the simple harmonic oscillation, or the motion of this object is simple harmonic motion. First we have to do this thing, and we have to obtain the equation of periodic time of oscillation. Clear? For that purpose, here we consider the spring obeying the Hooke's law. The one end of a spring is tied with a zip wall and other is tied with a block placed on a frictionless and horizontal surface as shown in the figure. For that purpose, like this manner, one end of the spring is tied with a ball, while the other end is tied with a block of mass M. Block of mass M is placed on a frictionless and horizontal surface. So that is the x is equal to 0 position. There is the x is equal to plus A. There is the x is equal to minus A. There is the plus A. There is the x is equal to minus A position. There is the rigid one. So as shown in figure, consider a spring one end is attached with a rigid wall and other with a block of mass M placed on a frictionless horizontal surface. As the block is pulled one side and released it performs the simple harmonic motion. When a block is pulled one side and released, it executes a simple harmonic motion or a simple harmonic oscillation. Simple harmonic oscillation. Now, in equilibrium position of a spring, the center of a block is considered as a mean position x is equal to 0. In equilibrium position of a spring, the position of center of a block is x is equal to 0, that means the mean position. Mean position. And x is equal to plus or minus a. X is equal to plus or minus a points, and at the displacement of a block is maximum. From Hooke's law. Now listen. During the motion of a block, the restoring force acting on a block due to the strain is directly proportional to the displacement and opposite to the displacement. Right? Now, during simple harmonic motion or during motion of a block, the restoring force act on a block due to a spring is opposite to the displacement and directly proportional to to the displacement. Thus, such oscillations are simple harmonic oscillations. Thus, such oscillations are simple harmonic oscillations. The strain force by the strain. Now we are going to derive the equation of periodic time. The strain force by the strain at x distance from a mean position is F is equal to minus Kx. X is equal to minus Kx. That is our equation number 1. Now from Newton's second law, of motion, F is equal to ma. F is equal to ma. Comparing equation 1 and 2. Comparing equation 1 and 2. First we compare these two. Therefore, MA is equal to minus KF. But acceleration A is equal to minus omega square x. Minus omega square x. Therefore, M minus M omega square x is equal to minus kx. But k is equal to. Now, what is the equation of the k? Wave vector. Already we know that m omega square. K is equal to what? M omega square. Now here the x-axis cancel. Minus minus becomes the plus. Therefore, omega square is equal to k by m. But omega is equal to 2 pi upon t. 2 pi upon t. Therefore, omega is equal to k upon m root. Therefore, 2 pi upon t is equal to square root of k by m. Therefore, t is equal to 2 pi under root of m upon k. Is the equation of periodic time of oscillation of a string and frequencies of oscillation. F is equal to 1 upon t. Therefore, 1 upon 2 pi under root of k upon m. K upon. So these are the equation of periodic time, t and frequency of oscillation of a string. There is, again revise it. So first we need to get the oscillation due to a strain are the simple harmonic oscillation. To prove this oscillation are the simple harmonic oscillation or the simple harmonic motion, the necessary and required condition for the simple harmonic motion is that the force acting on a particle performing the simple harmonic motion is directly proportional to the displacement and opposite direction of the displacement. If the particle performs the motion under such type of the force, so motion of this particle is known as the simple harmonic motion. For that purpose, we consider a spring. The one end of the spring is attached with a Z ball and other is attached with a block of mass M placed on the frictionless horizontal surface. When the block is slightly pushed, slightly pulled or the pushed and released, it performs a simple harmonic motion about its mean position. Clear? In equilibrium position of a spring, the center of a block is we consider as a mean position. While the x is equal to plus a and minus a, the displacement of a block is maximum in either side of a mean position. Now, during the motion of a block, suppose we slightly pull down and release it, so block is perform the simple harmonic motion on a horizontal surface. During this motion, the strain force act on a block due to a spring is opposite to the displacement and directly proportional to the displacement. Thus, the such oscillation of a block are known as the simple harmonic oscillation. The strain force by the spring at x distance from a mean position is F is equal to minus Kf. And now from the Newton's second law of motion, F is equal to ma. Comparing these two equations, so we obtain the ma is equal to minus Kf. But we know that during the simple harmonic motion, the equation of the acceleration is minus omega square x. Substitute here. So minus m omega square x is equal to minus kx, x cancel, therefore omega square is equal to k upon m. But the omega is equal to 2 pi f or 2 pi upon t. Therefore omega is equal to square root of k upon m, substitute the value of omega, 2 pi upon t, under root of k upon m, therefore t taken here, this here, therefore t is equal to 2 pi under root of m upon t. Is the equation of periodic time of oscillation of a spring. And the frequency of oscillation, frequency is the reciprocal of the periodic time. Therefore f is equal to 1 by t is equal to 1 upon 2 pi under root of k upon m. There is very easy. Only we have to compare the strain force and Newton's second law, and we substitute the required value.